One more quick note before we go into hypothesis testing. Permutation testing or permutation resampling testing is, so permutation resampling test. It is slightly tricky to get your head around. To be honest with you, when I first learned this, I actually learned this in the industry. When I first learned this, it almost took me 30 days to digest the concept completely. So many of you may feel that, hey, I only understood this partially. That's perfectly okay. If this is the first time you're hearing this or first time you're understanding this, that's perfectly okay. There is no worry about it. Okay, so please don't worry about it. It is only normal because this concept is slightly unintuitive, right? It's not straightforward to get it. So don't worry about it. Even if you have understood partially, think about all the stages: the combine, the shuffle, the resample, and computing the median, right? Think about these stages and ask yourself, what if I remove this? What if I remove this? What if I remove it? And so on and so forth. If you already knew this test earlier, then probably I hope you got a deeper understanding. Okay. Now, is there a problem? Is everything all right, folks? Can you just confirm? Is everything all right? Okay, no problem. Good. So now let's learn some terminology. We already have learned the concept of hypothesis testing. So permutation resampling test is one of the many hypothesis testing strategies that exist. Okay, I'll tell you why permutation resampling test is powerful, when to use it and when not to use it. Okay, we'll come there. But let's understand some terminology so that you can read research articles, you can read Wikipedia articles, etc. So there is something called as a null hypothesis, often written as H0. A null hypothesis, in our case, I'll connect everything to our case, is that the control and the treatment are the same. This is the hypothesis that we simulated. Remember, the null hypothesis, which one to choose as null hypothesis is slightly tricky. But in our case, in the case of permutation resampling test, the reason we said our null hypothesis is that XC and XT are the same is because we can easily simulate this and actually observe what is the value of the medians under this null hypothesis. Okay, so in the case of permutation testing, we pick the null hypothesis as something that we can easily simulate. That's the idea. Okay, so your H0, which is under this null hypothesis, we measured something. Similarly, there is something called as alternative hypothesis. The alternative hypothesis in our experiment was that XT is not same as XC. Not same. You could also have other alternative hypotheses that XT is greater than XC. This is also another alternative hypothesis, right? So for a given null hypothesis, there can be multiple alternative hypotheses. So whenever you're doing any statistical test or hypothesis testing, first you define what is the null hypothesis, you define what is the alternative hypothesis. In our case, the alternative hypothesis is that they're not the same. Then we define something called as a test statistic. What is it that we are measuring? What did we measure? We measured median difference. Okay, median difference between treatment and control. This is what is the numerical value that we measured, and we said, hey, this is the statistic which I will measure, and I will try to say, look at our whole test. In our whole test, we said, what is the probability that my test statistic, look at this, my test statistic is as extreme as observed, is as extreme as what was observed, as extreme as what was observed, which was M observed, under the null hypothesis, right? So your test statistic is what you decide. Again, there could be many valid test statistics. We picked this in our previous experiment. There can be many others. Okay. So in our previous example, the test statistic was the median difference between the treatment and the control. Cool. Now, similarly, again, what did we compute? We computed the probability of observing a value of the test statistic. So we test statistic. So we computed what is the probability of observing a test statistic value as extreme as what was empirically observed, which was MOBS, right? Which is the median difference which was observed under null hypothesis. Other way of writing it is, what is the probability of this M, this random variable M? What is this random variable M? It is the difference between medians under null hypothesis. What is null hypothesis? XT is same as XT or similar to XT, or the control and treatment are similar. This is same as what is the probability of observing my median differences as extreme or as large as the observed value or more. And we said this is 2%. That's what we discussed, right? This probability value is often referred to as the p-value. That's what it means. This is what the p-value means. A lot of people have a confusion what p-value. P-value is the probability of observing the test statistic value. Let me write it. The test statistic value as extreme as what we empirically observed under null hypothesis. When I say under null hypothesis, what I mean is, in the world where null hypothesis is true, in that world, what is the probability of observing this extreme value? Again, any mathematical equation that you encounter, please try to read the equation. A lot of people don't read equations in English. That's why they mess up everything. I've seen tons of even data scientists at good companies who mess up the interpretation of p-value. I have messed it up myself, by the way. I have no shame in agreeing to it, because I got confused in real situations. What the heck is this p-value? Then the lesson that I learned is always read it in English. Then things become easier. Okay. Of course, also understand the mathematics, but reading it in English will give you the frame of mind to think clearly and read it slowly sometimes. Okay. Then there is something called as significance level, also called as critical level. So what we do is this. The significance level that we're taking, typically that is taken is 5%. There is no rule that says you should always take 5% as the significance level. Now, what I mean by significance level is this. Okay, let me write it down for you. The probability, okay, so let me write this equation. So this is same as probability of observing my random variable M greater than equal to my observed value under my null hypothesis. Again, I'm writing it for our problem, right? This was observed to be 2%. This is empirically observed. We plotted the PDF. We did all of that math, right? Look at this. We did the whole math here. Just to quickly recap it for you, right? We resampled, repeated, got these M observations. We plotted the empirical PDF of this random variable M, which was a difference in medians, right? And we saw the observed value. We computed the area beyond this curve, and we saw that it is 2%. So all that is cool. Again, just recapping so that your context is correct. Now we say that, okay, I will pick a significance level based on my problem. Okay, I might say, hey, I'm going to pick a significance level of 5%. There is no rule which says you should pick 5%, but this is typically used. Typically, not necessarily always. Okay. Now we will say, if this probability value that you computed, what is this? This probability is nothing but your p-value, right? This probability is nothing but this p-value. If this probability value is less than 5%, I will reject null hypothesis. Why am I saying this? Why will I reject? Again, remember, what is my null hypothesis here? Null hypothesis is xt is same as xt. Okay, so that is your null hypothesis. Okay, so let me write it down here so that there is no confusion in that. Our null hypothesis is that xc is similar to xt. This is a null hypothesis. So we are saying, again, this, now the important question is, why did we pick 5% for this? So we are saying, if in this world, okay, we have a world here. In this world, the null hypothesis is true. This is a world. This is a worldview. This is a worldview. So what does it mean? It means xc is similar to xt in this worldview. Now, in this worldview, the probability of observing an M greater than equal to M observed, which in our case was 20, is very small. Again, in this worldview, this was just 2%. Now we say that for my problem, I will pick some number like 5%. And if this p-value or this probability value is less than 5%, I will say I don't think that this world is true. Okay, I will ignore H0 or I will reject H0. When you reject H0, you accept the alternative hypothesis. Again, this is the standard setup of hypothesis testing. So in our case, we got a value of 2%. Imagine, that's the key here. Imagine if we said that our significance level is 5%. If we said that, okay, I will say if this probability value is less than equal to 5%, I will reject the null hypothesis. When you say, what do you mean by rejecting null hypothesis? Which means I will say that this is not true. Which means you're going to accept alternative hypothesis. What is alternative hypothesis? Alternative hypothesis is XC is not equal to XT. Simple. Again, imagine if this p-value that we computed, it's not 2%, it's let's say some 10% we got. If this is 10% and if our significance level is 5%, then the p-value, which was 10%, it is not less than 5%. So we'll go into the else condition. Then we will accept H0. This is the setup. Now you might say, hey, all this is cool, but let's take another example, right? Again, same example that I just told you right now, right? So this probability value is 2%, which is less than the significance level that we set for this problem, which means we will reject null hypothesis. You would always state this very clearly. We are rejecting the null hypothesis at 5% significance level. Imagine we say, hey, I'm not keen on 5% significance level. I want to set my significance level at 1%. Let's assume you say that. If your significance level is 1%, then by applying this mechanism, you can't reject the null hypothesis. You will have to accept the null hypothesis because you're observed. Again, you did this whole probability computation, right? This is your p-value. Your p-value was 2%, and 2% is greater than 1%. So you will say that I will accept the null hypothesis, which means XC is same as XT at a 1% significance level. You never say I will accept null hypothesis or I'll reject null hypothesis. You always have to say at what significance level you're accepting it. That is the key, right? Again, no. So there is a very strong confusion that some of you have. One of the questions that I see here is p-value same as saying the probability that the null hypothesis is true? No, please. That's why I wrote this very clearly in English. P-value is the probability of observing my empirically observed, again, my test statistic value. The probability of observing my test statistic value as extreme as this. Now remember, this is what we discussed, right? If you have this world where we have a null hypothesis, where XC is same as XT, okay, let's think about it from a slightly different angle. This is our worldview. Okay, this is our worldview. In this worldview, the probability of observing the median difference greater than M observed, which is 20, is very small. In this worldview, it's 2%, very small. But remember, very importantly, in this world, there is still a 2% chance. In this world, there is still a 2% chance of observing this extreme value. It's not 0%, right? So when I'm rejecting my null hypothesis, there might be some error associated with it. That's the key. And I'll come to some few types of errors. So instead of saying p-value is a probability that the null hypothesis is true, there's a different way of thinking about it. Okay. So there are basically 4 types of situations. Okay. So let's think about this carefully. This is very, very important. This is also fundamental in machine learning. Okay. So let's take a worldview. Let's assume in the world, this is let's say ground truth. Okay, let's assume this is ground truth and these two are ground truths and these two are decisions made by us. Okay, let's assume. So let's assume H0 is actually true. That's a ground truth, right? Ground truth basically means that's the actual truth. And this is a decision that we took. So there are 4 possibilities. There is a world in which H0 is true or H alternative is true. Well, only one of them can be true, right? Both of them can't be true because they're often opposites of each other. Imagine if the null hypothesis is true and we accept the null hypothesis. We are not rejecting it. That's perfectly all right. We are doing the right thing. We should do the right thing there, right? The other way of looking at it. Imagine a world where the alternative hypothesis is true, and that's the truth. And we are accepting the alternative hypothesis, and that's perfectly all right. We should do that. So there is no issue with these two. But these two cells are the problematic ones. Imagine if H0 is actually true, but we mistakenly accepted the alternative hypothesis. Look at this. It is true. There is again, all this is probabilities, right? All this is probabilities. If you think about it, there is a probability that actually H0 is true, but we accepted alternative hypothesis. That's possible. There is a probability associated with it, and that probability so when we accept a null hypothesis, but the ground truth or the reality is that the H0 is true, that's called a type 1 error. So if you want to talk about any errors, you should talk in terms of type 1 or type 2 errors. Type 1 errors are also called as false positives. Why are they called false positives? Because I am saying that we are accepting the null hypothesis. So accepting the null hypothesis is taken as positive. This is taken as negative. While I'm accepting the null hypothesis, what I've done is false and incorrect. That's why it's called false positive. There's a second type of error. Imagine if actually the alternative hypothesis is true. The alternative hypothesis is actually true, but we accepted the null hypothesis. That's also possible, no? The other type of error. This is the actual reality, but we accepted null hypothesis. Then the error we get are called type 2 errors. They're also called as false negative errors. Okay, because we accepted the null hypothesis. We accepted the negative result, but we are false about it. Typically, in lot of hypothesis testing, this value is referred to as beta. This value is often referred to as beta. So you remember alpha is used for significance level, like 5% or 1% and things like that. This false negative, the probability of having a false negative is often written as beta. And if this is beta, remember, if this is beta, the probability, see, in a world, if HA is actually true, we either accept H0 or we accept HA. One of those two things can happen. If this is beta, this probability will be 1 minus beta, and that is often referred to as the power of your test. So what is the power of your test? The power of your test is, what is the probability that your alternative hypothesis is actually true and you also accepted the alternative hypothesis? That's called the power. Okay, standard terminology that's used. Okay, so okay, very nice. So this is how we use the errors. Okay, so power basically means how often do we accept the alternative hypothesis when the alternative hypothesis is true. Very simple question. Okay, so now another question that I have here is this: why are we choosing the p-value? Okay, this is a very nice question. Why are we choosing the p-value? Right, when you're computing p-value, you're comparing the p-value with the significance level. So I said we typically use 5% or 1% as the significant values. Now the question here is, why not? Very good question. Why not use some 90% here? Very good. Why not use that? Let's think about it, right? So what are we saying here? Again, always go to the first principles. That's a very nice question. Let's go to the first principles. What is a p-value? P-value is the probability of observing an extreme value. Okay. Again, I'll write it in short because writing the whole thing is harder. Probability of observing as extreme a value as we observed under null hypothesis, right? This probability. So imagine if I take alpha equals to 90%. Let's assume I take my alpha equals to 90%. When this is less than 90%, you're saying let's accept, when it is 90%, we'll say we will reject the null hypothesis. But that makes no sense, right? Now, why doesn't it make sense? Because look at this. What is a null hypothesis? Let's take our example itself, right? Our example is XC is similar to XT. That is a null hypothesis, right? Now, the probability of observing something this extreme, right? Again, this extremity you have to remember. The probability of observing something extreme will be very small. Why would it be this large? You got my point, right? So, okay, let me take a step back here. Let me take you through that PDF. Okay. So, okay. So let's assume if we choose, so this is a PDF of the median differences, right? If you choose an alpha value of 90%, let's say, okay, then what will you do here? Then you are saying, again, if my observed value was, if my observed value, okay, so let's assume my observed value was somewhere here. Okay. This sort of observed value is highly likely anyway under the null hypothesis, because this whole plot was plotted under null hypothesis, assuming that xc is similar to xt. This whole plot was plotted using that, right? And the observed value that you have here, because this area will be 90%, right? This area will be some 90% or so, right? So what happens now is this observed value is very likely, but still you're rejecting the null hypothesis. Why are you rejecting the null hypothesis? Just for the sake of rejecting? Doesn't make sense, right? Again, remember, the reason we take these alpha values to be small is because we're computing the probability of observing extreme values. Extreme values will not have high probabilities like this. They will typically have very small probabilities. That's why we take alpha values to be small and not large. Okay, that's the key idea behind it. Okay, so we have just introduced terminology now, nothing else. All we have done is what we have done earlier only. Whatever we have learned for permutation testing, we are just trying to frame it in the context of a concept and terminology. Because once we frame everything into the concept and terminology of hypothesis testing, we can learn many other techniques very fast. We don't have to go back to the drawing board every time. Okay, so cool. Now here comes another thing. Okay, so I think I've already answered this. This need not be discussed. So why did we choose our null hypothesis as xc equals to xt? I already answered that without even realizing that there is a question. We did this because this is easy to simulate and this is possible to simulate, right? If xc and xt are similar distributions, if they have similar distributions, I am just combining. So through the strategy of combine, shuffle, resample, right? Through this strategy, we can simulate this null hypothesis. Now the question here is, what if our null hypothesis was this? What if we chose a null hypothesis as xc not equals to xt? The question here is, how do you simulate this? There are many ways that xc can be different from xt. There are literally infinitely many ways. There are infinitely many ways in which xc and xt can be different. There is only one way through which xc and xt can be same, right? How will you simulate these infinitely many ways? It's impossible to do that, right? So it's again, think about it. So whenever we do any type of analysis on statistical tests, we try to get these four values. Again, oftentimes it's not easy to get these four values. Okay, that's what a lot of researchers try to understand. A very interesting research question is, what is the power of permutation test? It's not easy to figure out. It depends on a lot of things. For some simpler tests, right? So there are some simpler tests that make ton of assumptions. For them, it is easy. But for something as powerful and as chaotic, yet as impressive as permutation test, computing the power is not straightforward. There is some research on it, but it's not fully there. Okay. So the reason we picked xc equals to xt is because we could simulate it using permutations and resamplings.